This video is about adding the experiential element to the classroom. It's something that I notice does not exist in most classrooms. The purpose of the video is as follows. Courses generally teach an ideal or nominal approach. It's book learning. But outstanding systems engineers tailor the approach to fit the situation. So that's more than book learning, and that experience factor is needed in the classroom because we need to teach it to speed up the development of outstanding systems engineers. You don't know the difference between a systems engineer, a good systems engineer, and an outstanding systems engineer? That's in Module 3 of my course. The requirement, based on the goal, is to provide examples of when, how, and why to tailor the nominal approach, and to reflect on the example and the lessons learned from it. That's critical thinking. Now, as most of you know, there's generally more than one way of meeting the requirement. And so this is just one way of meeting the requirement. And this is the initial version of the exercise. And I write here which may be modified. It's probably going to be modified as time goes by. So the exercise is to tell a story. The presenter tells a story, describes the context or the background to tell us what's going on, so we have the big picture view. Describe the undesirable situation or the need, then how the presenter was taught to deal with the situation or not, as the case may be, which I'll discuss in the next slide. What was done about the situation, how the transition was made from the undesirable situation to the desirable outcome, why it was done in that way, what the outcome was, what systems engineers or system engineering or systems thinking tools, if any, were used in the transition and why they were used, alternative approaches that might have produced better outcomes, thinking about the whole story with 20/20 hindsight, and the lessons learned from the story. Those are the 9 basic requirements. The story may be from personal experience, that of a colleague, or a case study in the literature, in which case the citation is needed. And of course the story may be adjusted so that confidential or elements that the presenter does not want to share with the public are masked or left out. The time limit for the presentation is not specified, but you've got to make it short enough to keep the viewers interested. And the post-presentation discussion will focus on the critical thinking elements 7, 8, and 9. So, how the presenter was not taught to deal with the situation. An acceptable answer is, wasn't taught. That's what a systems engineer might say. But better examples from good and outstanding systems engineers would be, I found a way in a source and describe it. So even though I wasn't taught it, I took some action. As Howard Eisner says, good systems engineers take action. Or I found ways in more than one source. And by the way, they were the same or there were differences between them. And describe what you found and the differences and comment. You will find that there are differences in many systems engineering books and articles. And then another acceptable answer is, I looked in this book, and that book, cited, and couldn't find a way. Perfectly acceptable, but it shows that you took some action. That's how you get the A. An acceptable answer gets you a B-. How to tell the story. 1 volunteer per session, not per module, because some modules use more than 1 sessions. You can tell it verbally in class, which is less desirable, or you can use a recorded audio. You can put some notes that tell the story in the Facebook group. You can make a presentation in class, which is again not that desirable, but it's allowable. Or better off, put it in an online video on YouTube. My students at University of Maryland University College were creating offline videos in 1998 and 1999. And they didn't have the technology that we have today. Handphones were just about incorporating cameras at the time. Or find another way to do it. And the discussions will be asynchronous in the Facebook group that accompanies the class, which allows for thinking time. So I'm going to give an example, and I'm going to go a little overboard because I'm going to do it in my usual PowerPoint slides, using lots of slides, so you can read it as well as listening to it. It's personal experience that was also written up, so I put the reference here. And the original was presented at the Incosi Symposium in Holland, and so you can find the original article on my website, or in the Incosi database website, or you can see it in chapter 22, which is an updated version, in my book, A Framework for Understanding Systems Engineering, which is an anthology of papers that I published over the years. The context deals with decision-making steps in the problem-solving process, and particularly the analysis of alternatives in practice in a small system. The United States Department of Defense built up this function called analysis of alternatives in a very formalized version. Well, this is a small system, so we didn't use the formality, we just did the function. And the way to do it is the way we did it was identified 3 alternatives and then selected the best one according to the selection criteria. And it's in the context of the world's first solar-fueled electrical power generating system in 1981. That was 40 years ago. Wow. We had a large array of mirrors. The mirrors focused the sun's rays on an oil pipe to heat oil, and so we needed to track the sun's movement in the east-west direction. I'll show you a picture of this in a moment. The oil in turn heated water to create steam. The steam drove the electricity generating turbine. And this story needs with the need to measure the position of the mirror and the choice of device or technique or whatever you want to call it to measure the position of the mirror. So I'm going to discuss 9 topics, and the numbers match the story requirements, so it makes it easy to track them back to the requirements when I'm looking at the compliance matrix. The context. The context was Solar Electrical Generating System -1, SEGS 1, in the Mojave Desert in California, and we did the research in Jerusalem, Israel. We have the solar collectors here. There are mirrors. The oil is going through here. It's heating up. It's heated by the sun. It goes down here. It goes into a steam generator. It goes up here, and then it generates electrical power using the steam. And then there's the rest of the hydro mechanical parts that deal with keeping track of the oil, storing the oil, and cooling the oil down again so it can be pumped back through the system to generate heat. And if you want to see what the mirrors look like, this picture was taken well after the initial solar field was built. And they're big. This distance here, that's a person's height. So, what was the undesirable situation? Moving along. We needed a function in SEGS 1 to sense the position of each mirror to verify that it is pointing at the sun. So we chose to put that sensor at the mirror. So the problem was identify a number of different designs, build or buy, that perform the desired sensing function of the mirror, and to select one. Now the systems engineer is involved in such a decision because, first of all, the position sensor is a subsystem of the local controller that controls the mirror, and the selection of the design will impact the local controller system architecture and possibly the system architecture as well. So, how the presenter was taught to deal with a situation or not? Well, it's a decision-making process. So, the decision-making process is to conceive at least two candidate position sensors, candidate options, identify selection criteria, and then do the trade-off and make the selection using a variation of MVA to make the decision using the selection criteria with appropriate weightings. This is an example. The drawing is taken out of one of the Module 1 slides, and it's basically part of the problem-solving process. The selection criteria are pretty standard, actually. Accuracy. The system requirement is to point the mirror focus at the sun plus or minus 0.2 degrees when tracking. Complexity. What's the impact on the mechanical subsystems and the need for additional circuitry or software in the local controller and test equipment, and maybe even in the central station? Cost. Important. Luz is a startup venture, so raising capital is not that easy. The system is going to use 600 of them, and there are different costs, fixed and variable cost elements in R&D, in manufacture, test, installation, and operations and maintenance. And then, could we trade off a more expensive one-time manufacturing cost to lower the unit cost? Remember, we're going to multiply every unit cost by 600. So every dollar we save in the unit is $600 saved over the system. So saving $10, $6,000. Would that have an effect? Reliability is important because downtime due to failures means loss of revenue and cost to repair. Schedule. Must be ready on time. Note, there's a possible coupling between cost and reliability. If the reliability goes up, the cost will go up. Cost and complexity and reliability. We have to take that into account, or not, as the case may be. And one of the selection criteria I haven't written down here, which you must be blaring away in your head, is risk. If we're developing a sensor, whatever the sensor is, it's got to be low risk. We're taught develop or create the utility curves. And this is a picture of a utility curve from my book that talks about Fred, and it basically takes some subjective values for the type of person he's looking for. Is she an alcoholic, a social drinker, drinks sometimes at mealtime, rarely drinks or never, and assigns a number to it. So we can then use that number in the table, and you can notice that the shape of the curve shows that there's a strong bias towards somebody who rarely or never drinks. I'm not going to explain utility curves here. That's explained in a different class. So accuracy, first of all. The system requirement is to point the mirror focus at the sun plus or minus 2 degrees when tracking. But does that actually apply to the position sensor? Do we need to know the position plus or minus 2 degrees? Needs to be looked at. Complexity. The simpler the better. So what shape of utility curve should we use? Cost. The lower the better, and the curve is probably more logarithmic than linear because we've got a lot of these things. Reliability. The higher the better. Curve is nonlinear. What about risk? The lower the better, but what kind of utility curve do we use? The schedule, that's an either or. If it doesn't make the schedule, other criteria are irrelevant. So when we're going to make a selection, or when we're going to weight that criterion, if the candidate looks like it's not going to make the schedule, all the other criteria are irrelevant. And then the question is, once we have the utility curves, do we need to get consensus from all the stakeholders? And if we do need to get consensus, can we get it? Questions that are not asked or not raised in the textbook. So what did we actually do? Cover that in this section. There were 3 candidate designs. The first candidate was an optical pulse counter. You can look at it here, and you can see that there's a light emitter and a light detector, and then there's this spoke of the shaft that rotates in and out of the screen. And every time the spoke breaks the beam, it generates a pulse in the detector. Alternative could be a disc with a hole in it, and every time the hole goes between the light and the emitter and the detector, it allows light to go through, and in either way it creates a pulse. And the rotating spoke, it generates 1 pulse per revolution, and they were thinking about counting the revolutions or counting the pulses, and then calculating the position of the mirror. I had a bad feeling about this one. It was too complex, and it relied on calibration, it relied on a switch because you need to know where it reset, and it relied on mechanical coupling to the motor. And so we looked into 2 other conceptual designs, a potentiometer and an optical position sensor. So let's look at the optical pulse counter for a minute. I talked about that. The photodiode and detector generates a pulse, and the software counts the pulses and calculates the position. It uses minimum electronic hardware. Basically, there's the interface to the diode detector and a reset switch. And so all you've got to do is to amplify the diode output and digitize it and do some counting. It does need a mechanical interface to the motor, which is unknown at the moment. It also needs a stowed position sensor, so you need a micro switch on the mirror that is going to be used out in the field. So it's not just a simple switch, it's got to be sandproof and weatherproof and all that kind of stuff. And it might also require battery backup on the memory to store the count and position if the power fails. And that would depend on how much time it would take to determine the position after a power outage. So we need to know how long it would take the mirror to move back to the reset position and then start deploying again, and what the worst case would be and how much energy we might lose. So there's some calculations that need to be made, but we don't have any answers for them at the particular time that this decision had to be made. So again, it gave a bad feeling. There were unknowns in the custom manufacture, position certainty, could it be made in time, and what were the risks of not having it when it was needed, and also what failure modes. Risks, there are 2 sets of risks here. There are the process risk, in which could we manufacture it in time, and what about the failures once it's operating. The next one was the potentiometer, another thing that we build. It's mechanical coupling to the mirror in some way. It's an analog voltage because the slider on the potentiometer changes the voltage that is applied to the digital interface, but the digital interface is just an analog to digital converter, same as the diode pulse counting sensor. And you use a software algorithm to convert voltage to position. But when we think operationally, there's going to be wear and tear on the track section of the potentiometer, because this is going to be tracking every day. And what's the reliability and what's the lifetime under that situation? So the people who thought about using a potentiometer said, don't worry about that, we're going to use a missile part, because missile parts are highly reliability. Yes, but systems thinking says, wait a minute, there's a difference in the operational life cycle. A missile spends most of its life doing nothing. It's in storage. Then it has 5 minutes, or maybe longer, depends on where the missile is going, but well less than an hour of operational lifetime. Yet this is going to be using day in, day out. And so there are calibration issues, there are position tolerances, which are limited by the resistance tolerance. And again, there was at least I had a bad feeling about this because it's high risk. There are unknowns in cost of manufacture, in the reliability, the position certainty, and the schedule. There's too much to find out, and there's not enough time to do it. So the third choice was an optical position sensor. It was a commercial off-the-shelf device. It was digital. It had an 8-bit TTL interface. It gave you the absolute position. It was gray code, so there were no transients. I mean, it was obviously designed as a position sensor. And you could easily use a software lookup table for position determination. Simple, minimal risk, high reliability, but each unit cost $300, although the quantity discount did bring it down. And we were in Israel, and it had to be ordered from Japan. Those were the choices. How the decision was made. Selected the optical shaft encoder and ordered the prototypes. Totally ignored MVA and didn't bother with utility curves and didn't bother with a decision matrix. The reason for it was basically risk reliability, schedule certainty, and simplicity. It was the lowest risk. They existed. It was reliable. We checked with the manufacturer. We did some risk management to make sure that we could obtain them when we needed them. And it was simple. Zero complexity. All we needed was a digital interface between the microprocessor control board and the device. Why it was done that way? Well, the decision needed to be made before any useful reliability data could be gathered on the alternatives. Pulse counting detector was having mechanical difficulties, and I really didn't like relative position sensing. We didn't have any resources in the department to prototype and test the potentiometer candidate, even if we could do accelerated aging, but recognizing that this decision could be revisited in future product updates, and there was a lack of department resources in general. So once we had the system built and deployed, we might then take the time to actually run some experiments on the potentiometer and see if it could be made cheaper and as or more reliable than the optical generator. What was the outcome? Well, that was simple. The head of the mechanical department, Rogo, he simplified the mechanical design by taking the shaft, the optical encoder, and attaching a pendulum to the shaft. So the pendulum was always vertical, which whatever position the shaft was in. So all he had to do was to take the pendulum and the optical encoder, put them in a sealed box, and mount them on a mirror assembly, preferably in the shade. And there was no specific mechanical coupling needed. Very low tolerance on where it needed to be, low specification. We didn't even need an ICD. The optical encoder and the local controller were both TTL level signals. That's a known specification. The connector, we just designed the connector on the local controller to be the same physical connector as the one on the optical encoder. The cables and the connectors and the pin connections were shown in the design drawings, and the cable was a pin-to-pin connection between the identical connectors. Once we had the spec of the optical encoder, we knew which bit was on which pin, and so the printed circuit board layout for the local controller board was designed in such a way that the connector on the board matched pin for pin. No ICD was needed. They don't tell you that in the book, do they? So what systems engineering thinking tools were used? Analysis of alternatives, but only up to the point of feasibility. So instead of building that whole matrix, we looked at the risk and said, This one's too risky. Stop there. No point in going through the other ones. This one's not reliable enough. Stop there. No point, because we were only going to make this decision once. The books talk about building a table or a decision tree. But wait a minute. If you're only going to make the decision once you get a weighting that says the other options are not going to happen, there is no need to build the unused parts in the decision tree. Don't waste the time doing it. The only time you do use a decision tree is when the decision is going to change under different circumstances and the weighting is going to change. But the books in general don't point that out. So critical thinking. We used pulse counting is a good way to measure speed, yes, but it's not so good for measuring position. Decision making was a tool. And the other tool was one of the most useful for systems engineers, which is keep it simple. Reducing the complexity and increasing the reliability and minimizing the risk. And so we used also the tailored generic problem solving process, or the generic problem solving process tailored to this situation. So what alternative approaches might have produced better outcomes? Well, first of all, we need to know what a better outcome is. A better outcome would be one that has a lower cost, a higher reliability, and a lower risk, at least one or more of those three. And in the 40 years since then, every time I've thought about it, I haven't thought of any alternative approaches or solutions that could have done it any better. Feel free to propose one. Lessons learned from the story. Well, this was my first job as a project manager, and I found a dichotomy or a conflict. The engineers wanted to try out new and innovating and exciting ways of performing the function. The project manager wanted a solution with the lowest risk to the schedule, a tried and tested design. And so as the project manager, I had to encourage the engineers at the same time as turning down their ideas, which was interesting, especially as it was my first project management position. I'd gone from being a systems engineer and getting promoted into a project management position in another company in another country on a project that had a high risk of failure. Next lesson was keep it simple. The next lesson was requirement specifications and ICDs may not always be necessary. I learned that from the project because when I came into the company and I came into the project, the first thing I asked for as a systems engineer was, where are the requirements? And the response was, what's that? And I thought about it for a while, and I realized, hey, everybody knows what we're doing. We don't need the requirements. Think about it. Requirements communicate something. And if you can communicate something in a different way, you don't need the requirements. So we need to think about these documents, requirements and ICDs. We need to think about the purpose they serve, if they're necessary in the context, and if there's an alternative way of fulfilling the purpose. And this approach, this is the important lesson, the approach was tailored to the situation. It may not be suitable in other situations. And that's why I want to get lots and lots of stories for different situations. And that reminds me, years ago I was proposing to build a database of all these stories and put them online. But for one reason or other that never happened. So if anybody who's looking at this is not in my class but wants to share a story in this format, please get in touch. So here's a summary. I went through the 9 requirements, and you can see I talked about the context, the undesirable situation, and so on and so forth. And to my students, this is a demonstration of a compliance matrix. You can see what the requirements were by number, a little wording there to remind you of what the number actually was and which pages in the presentation contains the information that meets the requirements. Any questions, comments, and discussion? If you're in the class, post it in the class Facebook group. If you're not in the class, send me an email. Thank you very much for watching this video.